grandma died.
You're lying to make up you.
And I was like, well, then her grandma really did die later on. So I was like, please don't kill your relatives just to make excuses for the
I mean, I said that too. I was like, no dead relatives, please. And, no near brushes with death yourself. Like, if you're actually sick, let me know you're sick. And if you're not, don't let me know about it.
Yeah, I lied to them to tell them not to lie to me.
I know. Really confusing to me.
Okay, so I'll remind you where we were. We were talking about Mobius functions. And I defined the Mobius function for you last time. So I said that it's 1 for y equal to x. And then if y is bigger than x, then you basically add up mu of x comma z for all z between x and y. So this is if y is bigger than x. And I said that an equivalent way of saying this is that the summation, so if you fix, let me see what notation I want. I'm not sure what notation I'm going to want, but if you fix x less than or equal to y, then when you sum mu of x comma z for z between x and y, you get 0. And so we said this was somehow, you can think about this in the poset. So if this is my poset P, this is x, this is y, and so the interval is the things here in between. And so we're basically saying that if you add up mu of x comma something for each something in this interval, you get 0. Okay, so this was the definition of the Mobius function. And then I had stated the Mobius inversion formula. Which said that if you have two functions from the poset to some ring, which I said maybe is the integers, but it could be any other ring. And if the first function just adds up f of y for y less than or equal to x, then you can reverse this and write f in terms of g. The only thing you have to do is stick the Mobius function here as coefficients. Okay. So if this is given, if g of x is given by this for all x in P, then f of x is given by this for all x in P. Okay? And so I want to start by proving the Mobius inversion formula. I stated it last time, and I showed you why it was, even though it's a little bit difficult to parse, it's an extremely useful formula that people use in number theory. People use it in inclusion-exclusion for counting problems. So now we're going to prove it. So proof. Okay. Well, I'm basically just going to compute this sum and show you that it's equal to f of x. So let's compute for a fixed x in the poset. Let's compute this big sum. Well, I'm going to take g of y and just apply the definition of what g of y says. So g of y adds up the function for all c's that are less than or equal to y. This is just this equation right here. And I get this. Okay. And now, so I have a summation of a summation, and what I'm going to do is flip the order of the summands, which we know we can do. So the z's that we are considering are all the ones that are less than or equal to x. And I get now if I first sum over the z's, then I get all the z's that are less than or equal to x. And if I sum over the y's, then I have to pick up the y's that are bigger than or equal to z and smaller than or equal to x. So I add up over the y's between z and x. Okay. Maybe to make it clear, in each one of these summations, I'm going to say which variable I'm adding over. So x is fixed. Here I was adding over y. Here I was adding over y. And here over z. I flipped. So now I add over z. And this is a sum over the y's between z and x. Okay. Now, what I want you to notice is that this thing that I'm adding up, f of z does not depend on y. So I can factor like this. Okay. So I haven't really done anything yet. But then the point is that I want to compute this sum over here, which kind of looks familiar, right? So I'm summing over the y's in an interval between z and x. I'm summing Mobius functions. Okay. Now, actually, let me first modify my equation here. So for x less than y, it says this. And for x equal to y, what do I get? If x is equal to y, then what is this sum equal to? Well, I'm adding over the z's that are between x and y, but x and y are the same thing. So really, I'm adding up only one z, which is x. I'm adding mu of x comma x, which by definition is 1. So this sum that I'm considering, the sum in an interval, is 0 if the interval is not trivial, and it's 1 if the interval is trivial. Okay? So here I have my sum over the interval. And I want to say that this sum is 0 if the interval is not trivial, and 1 if the interval is trivial. 0 if z is less than x, so there actually is an interval there, and 1 if z is equal to x, and so actually there's just one summand. Okay? Once I do that, I'm basically done, because what this is saying is that this blue sum over here is almost always equal to 0, except it's equal to 1 when z is equal to x. And when z is equal to x, I get 1 times f of x. Which is what I wanted to show. Okay. So there's a proof. Is that a proof? sure? You sure this is a proof?
It's a loaded question.
I think I pulled it. I pulled a trick. You guys didn't notice that I cheated. And I think the problem is that there are so many symbols that you didn't notice that I pulled the trick in saying that this is that sum over there. Because this that I wrote here is not that sum over there. It's almost, but it's not.
It's not in a pretty critical way.
Because here I'm adding over the variable y, and I'm adding the values of mu of y comma something.
Right.
But here, I'm adding over the variable z. Let me maybe bring my blue marker over here. Here I'm adding over my variable z, and my variable z occurs in the second position in the sum. So I cheated. Chris?
In this one, the something is the lower bound of our thing we're summing over, and there it's the upper bound.
Remember that the way that I described this is that you look at the poset, you fix x, you fix y, and now for each z over here, you add up the Mobius function of x comma z. But what's the picture over here? It's the opposite. In this sum, what am I doing? Well, I have my poset, I have my interval. So here's x. Sorry. Now z is the lower bound of the interval. X is the upper bound of the interval. And over the whole interval, I'm picking y, and I'm adding mu of y comma x, which is, if y is here, I'm adding the Mobius function in that interval. So it's almost the same sum, but it's not the same sum. So I cheated.
But it's going to have the same. But if you look at that picture,
If I look at this picture,
if you add up that interval,
I mean, the point is that it is very close, but it's not the same.
Right.
And so this is almost a proof, but it's not a proof. And if I want this to be a proof, then I need to show what I said here. 0 if z is less than x, 1 if z is equal to x. This is what I need to show. Because this is what I used. Now, hopefully this is true, right? It looks like it's true because what I want to get is f of x. I'll be done if I can prove this equation, which is the next thing we're going to do. That even though I defined the Mobius function to talk about kind of lower blue intervals inside that black interval, it also has that property with these upper blue intervals in the black interval. So I'm going to prove this. And again, I'm going to try to keep doing this. If I forget, remind me to write under each summation the letter that I'm actually summing over, because it's going to get a little messy. So proof. How am I going to prove this? I'm sorry? The proof is just a matter of kind of computing and seeing that it does compute. Okay? So what I'm going to do is this. Let's fix z. I mean, this is a statement about z and x. So let me fix z, and now I have to prove it for all the x's that are above z. And what I'm going to do is something that you might call poset induction. But what I'm going to do is prove it for x. I mean, I need to prove it for z and the things above z. So I'm going to prove it for z, then I'm going to prove it for the things above z, then I'm going to prove it for the things above those, and I'm kind of going to work my way up those. And so I'm going to say induct on x greater than or equal to z. This is how you do this kind of poset induction. So the base case is the first one, which is x is equal to z. So I need to just compute the summation for z less than or equal to y less than or equal to z. Y is the variable that I'm summing over, of mu of y comma z. What is this equal to? Well, if y is squeezed between z and z, then it can only be z. So this is mu of z comma z, which is 1, which is what it should be. Okay? So that's done. Okay. And now for the induction step, what is it that I do? Well, basically, let me think about it this way. So here's z. Here are the things that are above z. And I'm thinking that I'm working my way up. So I already proved it for this guy, for this guy, for this guy, for this guy. And now I want to prove it for some guy here, x. So I'm going to assume that I proved it for all the things that are below x, and then I'll prove it for x.
So I have a question about just how you're phrasing this, because I had the same problem in the homework trying to phrase something. When you're saying proving it for all the a's less than x, or you're assuming you have it for all the a's less than x, you're actually, by your picture, assuming you have it for more than that. Like, you're having, the way you've got it for lots of things that are not necessarily ordered with x at all.
Right, so really I'm assuming that I have it for these guys that are kind of between x and z.
Okay. Okay. Great.
And I'm going to show it for x. So here's the summation that I want. And I'm adding over y of mu of y comma x. What's mu of y comma x? Well, by definition, it's that summation over there. Mu of y comma x is minus sum for z less than or equal to, sorry, mu of y comma x. So y less than or equal to a less than x of mu of y comma.
And it's a we're summing over now.
And we're summing over a. When am I justified in saying that this expression over here is equal to this expression over here? I'm justified if
Y doesn't equal.
if x is bigger than y. But I'm not justified in doing this if x is equal to y. So I have to do the case for x equal to y separately. For x equal to y, I just get 1. So what I said is this, that I'm writing mu of y comma x as minus this big sum. But if you look at my defining recurrence over there, I can only write mu of something comma something equals minus a sum, where the something comma something are different things. Y and x are different things. If they're equal things, in the case y is equal to x, I just get 1. So that's that one. Okay. Now, again, what I'm going to do is just invert the order of summation here. Okay. So first, let me sum over A. So what A's can appear here? Well, A is something between y and x, and y is something between z and x. So therefore, A is between z and x, and A cannot be equal to x. Then I get summation over y. And which y's am I adding over? They are the y's that are less than or equal to A and bigger than or equal to z. And I get minus summation of, no. I get minus mu of y comma A. And then plus 1. But now, what is this sum? Well, what I'm doing is, for each y in the interval between z and A, so again, I draw my picture. Here's z, here's A. I'm considering all the y's in between and adding up mu of y comma A. I'm adding up this. So what can you tell me about this sum? Well, it's exactly the same kind of sum that I'm trying to compute, except here I'm computing it between z and x, and here I'm computing between z and A. X is up here somewhere. In other words, this sum right here is one of the ones that I have by the induction hypothesis. Because I'm trying to get the sum from z to x, and I said, assume that I know it between z and A for any A less than x. Okay? So this is exactly my induction hypothesis. And my induction hypothesis says that this is equal to 0 if A is bigger than z, and 1 if A equals z. Now it's 1, but it would be 1 if I didn't have the minus sign. So it's minus 1 if A is equal to z. So what do I get here? For each, whenever A is bigger than z, the summand here is 0. This disappears. And when A is equal to z, I get a negative 1. So what I get in the end is negative 1 plus 1 equals, which is what I wanted. And that's the end of my proof. So that proves my lemma that I had over there, and that proves my Mobius inversion formula. So that's the proof. As I told you guys, that there's not a lot of clever ideas here. This is just a matter of writing it down and going through the motions and seeing that it all checks out. I think the biggest challenge here is to not get lost in all the notation. Okay. But this is necessary so that now we can actually use Mobius inversion, and now you can use it in your homework, which you need to use it in your homework. And we will keep using Mobius inversion in the class. Okay. So let's now go back to the Mobius function that I was talking about here is the two-variable Mobius function. But originally I defined the Mobius function to be a one-variable function. And that already we saw is interesting. And so let me just remind you. Let's see where I should draw this. I'm going to draw it over here. So the poset that we keep looking at. This is a geometric lattice, and I'll show you why. Well, first of all, because it's the same one that I always draw, so you know it's geometric already. But if I label it like this, I can just give you a geometric representation of this lattice, which again we have seen before. And to give you practice with affine representations, I'm going to write it like this. So basically, what I'm saying is that 2, 3, and 4 are a flat of rank 2. So that means that 2, 3, and 4 are 3 points on a line. So they are dependent. And then 1 is here. The flats that you see in this picture, I mean, if you want to get the flats here, what you have to see is what are the lines, planes, etc. that you can draw. So the points are 1, 2, 3, and 4. What are the lines that you can draw in this picture? 1, 2, 1, 3, 1, 4. 2, 3, 4. What is the plane that you can see? 1, 2, 3, 4. The same one we keep talking about. Any questions about this? About why this affine representation gives you this matroid?
Where did the 2, 3, 4 line that you originally, the black one, where did that come from again? The one that you started off with, you put 2, 3, 4.
So the thing is that remember these are ranks, right? So 1, 2, 3, and 4 have rank 1. That means they're not loops. 1, 2, 1, 3, and 1, 4 have rank 2.
I got it. Okay.
But now 2, 3, 4 have rank 2, which is why I have to put them on a line.
Thank you.
Okay, and so what we did is we said we can compute the Mobius function of this guy. 1, minus 1, minus 1, minus 1, minus 1. 1, 1, 1, 2, minus 2. What we do is at each point, you just add up the things underneath, you flip the sign. And we said that if you just add up by rows, you get, here you get a 1, here you get a minus 4, here you get a 5, here you get a minus 2, and you build a polynomial out of these, which is the characteristic polynomial. These are the coefficients. You get q cubed minus 4q squared plus 5q minus 2. Okay. Now, And so I said in general, the characteristic polynomial of a matroid is just adding up for the lattice of flats the Mobius number q to the r minus the rank of f. So we said that this was the characteristic polynomial. So this is the kind of the official definition, and this is really how you would do it in practice. Okay. And what I want to illustrate to you guys now for the next couple of classes is why this is such an interesting polynomial. And one justification that I gave you is that actually we also had a graphical representation of this matroid, where, again, the idea is that I have to put 2 and 3 and 4 to form a cycle. And then 1 doesn't form a cycle with anything. So this is the graphical representation of this matroid. And what I mentioned to you guys and what you are going to prove in your homework is that this polynomial counts colorings in this graph. So if you're interested in counting these proper colorings, which people are, then it's kind of inevitable that you'll think about this polynomial. Okay. What I'm going to show you now is yet another place where this polynomial appears, which is pretty amazing. So what I want to start by doing is giving you, here we have an affine representation of the matroid. Here we have a graphical representation of the matroid, and I'm going to draw the matroid as a hyperplane arrangement. So I'll remind you how that goes. The idea is that each element has to be a hyperplane. And you have for example, hyperplanes 2, 3, and 4 are supposed to form a circuit. And what that means is that you're going to have this is going to be this guy has rank 3, right? So here we have a 3-dimensional picture. So I'm about to draw a configuration of hyperplanes in R3. And the fact that 2, 3, and 4 are a circuit are going to say that 3 of the hyperplanes, generally if you draw 3 hyperplanes, then they intersect like the coordinate hyperplanes, and they have a common point. A circuit means that the 3 hyperplanes kind of form a fan, and they have a line in common. Okay. So we drew this like this. Here's one hyperplane. Here's another hyperplane. And here's another hyperplane. Okay, so these are 3 planes that are in a very special position because they all contain the same line. And this doesn't happen at random. I mean, at random, if you pick 3 hyperplanes, you're going to get like this, a floor, a wall, and a wall. They're going to intersect in a point, which is the vertex. But these are special because they intersect in a line. Okay? So I want these guys to be my hyperplane 2, 3, and 4. And then I want to consider another hyperplane, another plane, and I'm going to let it be this one over here. This plane is going to be my plane 1. So it's like the floor of this. We've seen this before. So is everybody seeing this picture? Should it look 3-dimensional to you? Hyperplane plane 1 should look like the floor, and actually this line is also on the plane. Okay. And then 2, 3, 4, and kind of 3 triangles sticking out. Okay. So what we said is that a hyperplane arrangement determines a matroid. This was part of homework 1. And let's remember how that matroid is defined. So A is a hyperplane arrangement. And we said that this defines a matroid where the ground set is A, and so you have to define dependence. And we said that you can define that a bunch of hyperplanes are independent. Do you remember what we said? What's the definition of independence? We said it in 2 ways. So one way is that we talked about codimensions. So we said codimension of, if you intersect k hyperplanes, then each one should drop your codimension by 1. So when you intersect k of them, you should get codimension k. And we said that was equivalent to saying each hyperplane has a normal vector. And we just said that independence of the hyperplanes is equivalent to independence of the vectors. Normal vectors v1 and up to vk are linearly independent. So here was the hyperplane arrangement. We got a matroid out of it, and then we got a lattice of flats. Any matroid has a lattice of flats. But I'll remind you that we said that the lattice of flats was actually very easy for hyperplane arrangements because the flats are just the intersections that you see in the picture. So we just said that this is the poset of intersections. Of A. In other words, if I give you the hyperplane arrangement and you want to find the lattice of flats, then all you have to do is look at this picture and look for how things intersect. So for example, the first thing you get is that you get the 4 planes. Each plane is just the intersection of a plane with itself. So you get 1, you get 2, you get 3, you get 4. And that gives you these elements 1, 2, 3, and 4 in the intersection poset. Now you're going to look at how you can intersect 2 planes. Okay? So for example, what is the intersection of 1 and 2? Well, here's 1, here's 2, and they intersect on this ray right here, this line. So this right here is the line 1, 2, which I should put in my poset. This one is the line 1, 3, that I should put on my poset. This one is 1, 4. And now we notice that something strange happens with 2 and 3 and 4, because no matter which 2 we intersect, we get this line right here. 2, 3, 4, which is this one. Now you might complain that you see more lines than I talked about, right? For example, here's a line in this picture. Why didn't I put this one in my intersection poset? It's not an intersection of anything. This is just a visual aid, so you guys see the 3 dimensions here. But this is just some random line that I drew on this plane. It's not an intersection of the other guys. Okay. Finally, when I intersect all of them, 1, 2, 3, and 4, I get this point right here. And so that's how I go from this picture of a hyperplane arrangement to this picture of a geometric lattice. Okay. Now, the idea of hyperplane arrangement, of a good part of hyperplane arrangement theory, is that you want to be able to obtain information, geometric information about the arrangement from combinatorial information about the poset or the matroid. The idea being that these things are very difficult to visualize geometrically, and these things are easier to play with. They're more concrete. Here's a poset, and you can draw it on your piece of paper. Okay. Let me give you an example of a question. Okay. Here's a hyperplane arrangement. 4 planes in R3. Okay, that's not too bad. It's one of the simplest arrangements I can think of. How many regions do you see in this picture? I mean, the point being, each hyperplane splits into this side of the hyperplane and this side of the hyperplane. So I drew 4 planes, and that cuts up space into pieces. How many pieces do you see? So there's 5. Which 5? There's kind of one that goes like this and another one that goes like this. There seems to be one that's kind of sticking out this way, one that way, and one back here. But these are the 5 that you're seeing. It's hard to see what.
Gesticulations aren't.
So you see 5. Okay. Does anybody see more than 5?
Yeah.
12.
What? Sorry, Federico. What are we counting as regions here? When you say regions, are we?
So what I'm saying is this: that each plane. I mean, basically, I just threw a bunch of planes into 3-dimensional space.
Sure.
So how many regions did I cut up the space into?
Okay. Well, I see 2.
1, 2.
Plane 2, 3, 4.
But they're all
One's
cut
cut
into
in half.
2.
And then they're all extending that way too. So it's
4. They're all cut into
So whatever you see in this direction is also going on in this direction.
right.
Okay, so if I give you some time, you can do this, and you'll have to do it about 3 times. And when you get the same answer 3 times, then you'll be convinced that you did it right. But this is for 4 planes in 3-dimensional space. This is completely unreasonable if that's so hard to do. The answer is so Jeff is right. There's 12, and you probably don't see them right now. I wouldn't see them. I can't see them.
Jeff, how do you find them?
It's like an asterisk into asterisk solve and you could have.
So the 2, 3, 4 is the asterisks. And then you
So what Jeff is saying is that this is not the right way to look at it. Really, I should think of 2, 3, and 4 somehow being like this: 2, 3, 4, and they're just like this thing coming out of the board. The common line is this line sticking out. And so I have 2, 3, 4. And now you can see it. One is the board. And so I get 6 regions over here and 6 regions back there. So this right here is 1. And I mean the board is plane 1, and 2, 3, and 4 are sticking out along this line that I can't draw. Okay, but so really now you look at it, and this is one of the easiest arrangements you can think of, and even that was hard. Fortunately, we don't have to do any of this. So let's say you have an arrangement in Rn. Let's say that it cuts up space into regions. Then the number of regions is just, well, I just erased this, but as you see here, I have a hyperplane arrangement. I have an intersection poset. The intersection poset has a characteristic polynomial. Plug in -1. That's it. So if L sub A is the intersection poset. And to get the number of regions, you just take the characteristic polynomial and plug in -1. And if you get the wrong sign, you just change the sign. So this is really a crazy theorem. So you plug in -1 here. You get -1, -4, -5, -2 equals -12. 12 regions. Okay. That's the theorem. It's the theorem of Zaslavsky from the 70s. No, I mean, so really, people just didn't know what the answer to this question was. And I think what happened really is that no one imagined that the answer could be so simple. And this is just incredibly simple. It tells you if you can compute this guy, then you're set. You don't have to think about geometry. You just look at the intersection poset, compute this Mobius function, plug in -1. So I think that's good justification to care about what these characteristic polynomials are. You might also ask yourself, out of these regions, how many are bounded? Okay. So staring at that picture, and more so staring at this picture, you can convince yourself that there's no bounded regions. But in other cases, there might be bounded regions. So let's say that R of A is the number of regions, B of A is the number of bounded regions. Well, Zaslavsky's theorem also says if you want the bounded regions, then you just plug in 1. Okay. So for example, here you plug in 1, and you get 1 minus 4 plus 5 minus 2 equals 0. Which is good because we didn't see any bounded regions.
Yes. Stop me if I'm wrong. But if I plug in 1 to the characteristic polynomial, I think I'm always going to get 0 out. Because I mean, if it looks like this, so it must be that somehow or other I've got a poset that's not a geometric lattice. It's like my poset's going to look different from this. It's not going to have a minimal or maximal element or something.
So, right. So what Kim is saying is that actually, when you plug in 1 into the characteristic polynomial, you're always going to get 0. The reason being that if you plug in 1, then all you're doing is adding up the Mobius numbers. And they add up to 0 because they're the numbers from the bottom to the top. But that's kind of weird because I told you that sometimes you do get bounded regions. And it's easy to draw an example. Like, here's R2. Here's an arrangement with bounded regions.
Did they have to go through the origin over here?
So that's precisely the point. I mean, the point is that here, well, these guys do not go through the origin. Okay. Let's figure out what the intersection poset is. So 1, 2, 3, 4, then empty. Then here's point 1, 2. Here's 1, 3. Here's 1, 4. What happened? Well, 1. So I should label it. This is 1, 2. This is 1, 3, 4. So 1, 3, 4 really goes like this.
Yeah.
And the one that I said was 1, 3 is actually 2, 3. This one is 2, 4.
But it doesn't have a,
And you see what happens. It doesn't have a top. Okay. Let's find the Mobius function here. 1, minus 1, minus 1, minus 1, minus 1. This guy has 2 negative 1s and a 1. So 1. This guy has 3 negative 1s and a 1. So you get a 2. This guy has 2 negative 1s and a 1. So you get a 1. This guy has 2 negative 1s and a 1. So you get a 1. So the polynomial you get is q squared minus 4q plus 5.
no, you put in more negative two.
This is no accident that I chose to draw this guy, because really, yeah. So what Jeff is saying is exactly right. This is just taking my arrangement over there and just taking a cross section. Yeah. What is chi of 1? 1 minus 4 plus 5 is 2. 2 is the number of bounded regions. What's chi of negative 1? 1 plus 4 plus 5 is 10, which if you count them, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, it's the number of regions. Okay. So what did Kim show here? That basically, if you have a central arrangement, then it has no bounded regions. Because if you have a central arrangement, the central arrangement has a top element. And if you have a top element, then plugging in 1 gives you 0. So there's no bounded regions.
Federico, what kind of arrangement are you calling if you have a what arrangement and a central, or they just say the central?
I said the word central. So central means that it's like that everything intersects. So there, all the planes go through a common point.
Okay.
Here, the planes do not go through a common point.
And then the lattices look different too. I mean, like, you don't have a maximum point.
So there you have a lattice, and there you really have a matroid. Here you don't have a lattice. You have something called a semi-lattice. And you have something called a semi-matroid also. All right, let's stop there.
Matroids, anyone?
Yes, absolutely. Actually, I have to meet with Dr. Lee, so I'll be up on the 9th floor.
Did you?
He's in today. We're
I kind of-
doing a group
I
meeting,
kinda gathered
so
from
whether or
the
not he
email
says,
about
let's do
W.
more, let's not, I might have to say it's not, but I don't want to get
Good luck.
I'll be up on the 9th. What? No. Do you want to ask? I need to run. I'll